Chapter 9, was it? Okay. So the question, as I just scribbled up all the notes up here, the question want to know basically how many milliliters is needed to make basically a 3.15 molar sodium bromide solution from 84.4 grams of sodium bromide. So basically, this is obviously dealing with molarity, as we talked about, and molarity is moles per liter. So really, we want to kind of think about excuse me, what was given to us. So in this problem, they obviously gave us the molarity. So we do have the molarity, which is 3.15 molar. We are also given the grams of sodium bromide, which is 84.4 grams. Now, what we can get from grams is we can convert grams into moles using the molar mass, which means essentially what they gave us was the moles, also the molarity. It's basically given to us. So we could rearrange the molarity sort of formula here to solve for liters. And if we multiply liters to the other side and divide by the molarity, basically liters would equal moles divided by the molarity. And that's good because ultimately what we're looking for, right, is milliliters. So not exactly liters, but we could definitely convert from liters to milliliters when it's all said and done. So one of the first thing we might want to do is convert our grams into moles. So we got everybody in the right unit. To do that, we would go to the periodic table, which I'm just going to hope is still 2299 for sodium and about 7990, I hope, for bromine, give or take a little bit there. So to get the molar mass for sodium bromide, we're really just going to add those two numbers together. And if we do that, that would be 2299 plus 7990. We'll call it about 102.9 grams per mole. And this would be the molar mass from the periodic table of basically NaBr. Any questions on that there? The reason really we need to calculate that is we're going to use that to convert our grams into moles so we can get everybody in the right unit. So that is really what we would want to do first here is take our 84.4 grams of NaBr. We would use the molar mass we just go on the bottom. Cancel, and that would get us 84.4 divided by 102.9. We'll call it 0.820 moles of sodium bromide. Again, the reason we did that conversion is that moles, which is what we need for molarity. So now we have, again, the moles and we have the molarity. So once again, just a rearrangement of this to solve for it. Also remember that we talked about when you're dealing with molarity and that big M, it's really important to think of it as like a conversion factor and do some dimensional analysis and really get rid of the big M. And what I mean by that is if you have 3.15 big M sodium bromide like we have in this case, that is the same thing as saying you have 3.15 moles of sodium bromide per liter. And you can really use it as a conversion factor if you needed to in dimensional analysis, flip it on its head. You could put a liter up on top, 3.15 moles of sodium bromide on the bottom. When you break molarity into those two units, it's really important because you can see the two units, you can see the moles, you can see the liters. And I said, I probably mentioned when we went over it, you should definitely do that because very common people will look at this big M and go moles. Because it starts with an M, so why not? Moles sounds like a good one. And either A, have no idea that there's actually volume there like liters, or if they do know that it is volume, they really have no idea as to, is it on the top? Is it on the bottom? Should I multiply? Should I divide? So if you get rid of the big M when you're doing a calculation, really treat it more like a conversion problem and just kind of keep both units, you most likely will not sort of mess up on it because you'll be able to kind of see everything. So that's how I'm going to really actually do this calculation is I know that I have 0.82 moles of sodium bromide. I'm going to use my molarity as a conversion factor. So I want to go opposite so that the moles cancel. So I'm going to put 3.15 moles of sodium bromide per liter. The moles of sodium bromide will cancel and we will get 0.820. We're actually dividing here by 3.15, which is exactly what we talked about doing here, dividing. And that gets us 0.260 liters. And that would be how many liters of sodium bromide would be needed. In this particular case, though, it was not looking for liters. It was looking for milliliters. So we do have to do one more conversion, that there are 1,000 milliliters in 1 liter. So on the bottom would go 1 liter, up on top would do 1,000 milliliters, and that would get us 260 milliliters of sodium bromide. Maybe with a point there for sig figs. Any questions on any of those steps? So it really is important when you're doing molarity, a couple things to remember. Like I said, really just automatically get rid of that big M, use both units so you can see it. And a reminder that if you are using volume and molarity together, the volume has to be in liters, in order for everything to properly sort of cancel out correctly. Any questions on that there? Other questions on, say, molarity or whatever, any of that stuff? Yeah. Yes. So let me answer it. I won't use the exact numbers because honestly I can't remember all of them. But I'll tell you what you're really doing in this problem, although it's wrapped in a lot of stuff in that one question, it's really a dilution problem that's doing. So if remember, we talked about dilution, and that is our M1 V1 is equal to M2 V2, if you remember that equation. So this is usually like before the dilution. This is like after the dilution, basically. Now, when you specifically use this, which will maybe answer part of your question, when you specifically use this equation in terms of the volume, you can leave them in milliliters as long as they're milliliters on both sides, or you can convert it to liters as long as they're liters on both sides. So because you need to use this, this would then, you have an option as to how to do it. So I believe, if I'm not mistaken, they gave you basically the final volume, right? But you do have a couple of things that, like you said, you do need to get it. You had some milliliters, and then you also had some microliters, I think, right? So you do have to kind of get these guys into the same unit before you add them together. So it might be easy just to convert that into milliliters and then add them together to get your final volume, which at that point you could either leave, like you said, in milliliters, or you can leave it in liters or convert it to liters, whichever way you want to do it. The original volume of what they like pipetted in, right, into like the 2 milliliters of water, that volume was also, I think, in microliters, if I'm not mistaken, right? Was it in milliliters? They like took a small sample of it, right, and put it in the 2 milliliters. Okay, so whatever unit the original sample was, you need to also get it to the same volume unit you have over here. So if you choose milliliters on the right, you should make that guy milliliters. If you choose liters on the right, you should make that guy liters. So they need to be the same units, whichever one they are. And then they gave you the concentration of the diluted sample, right? I think that times 10 to the minus 6 number, I think. So that would be that one. And they were asking what the original concentration was, correct? So you'd be solving for M1 in this case. I don't know. So you would just got to watch the unit. So you would be M1 should be M2 V2 divided by V1. And again, you got to make sure that the final volume, you get both of these guys to the same units and then add them together. So the final volume in this case was, right, they had 2 milliliters, I think you said, right? But then they added something to it. So you got to make sure you add those two together in the same units, and that would be your V2. And then the M2 would be the times 10 to the minus 6 number, I think you said. And then the V1 would actually be how much they added to the 2 milliliters of water. So whatever that number was should be V1. Yeah, so read me it real quick, just one more time, just the part where they said they added it to 2 milliliters. Two milliliters. So this is the part here. So this 100 microliters is really your V1, but you need to make sure it's in the same units as your V2. But V2 should be 2 milliliters plus the 100 microliters would be your V2, because that's what the final volume would be. And you got to make sure that, again, they're in the same unit. Whatever unit you want to choose, it's got to be the same unit. You could actually convert them all to microliters if you really want to, but probably milliliters would suffice. So what I would recommend is convert this guy to milliliters. And then once you have it converted to milliliters, you're then going to add it to the 2 milliliters here, and that would be your V2. And then your V1 would be the conversion there. And then your M2 would be the concentration that you read. And then you should be hopefully in business at that point. Yeah. Yeah, because that's the more concentrated solution, right? That they diluted. So it's like when we talked about, for example, I think we did like sodium hydroxide. We had like 19 molar sodium hydroxide, and then we took it out a certain amount and we put it into a new container. So in your case, the really more concentrated guy was the guy that they kind of pipetted into the 2 milliliters of water, because by adding it to the 2 milliliters of water, that basically diluted it, right? And it lowered the concentration there as lower. So did they give you the conversion for micro? Micros 10 to the negative, was it 12? 6. Was it? Micro negative 6, right? Okay. So in this particular case, well, let's get rid of this here. So basically, the original V1 was 100 microliters, which is 10 to the minus 6, which is micro. And that means that 100 microliters in 1 microliter, there would be 10 to the minus 6 liters would be the way that you would do that. And that would get you 100 times 10 to the minus 6 gives you 0.0001 liters. And we want milliliters. So we're going to do the conversion to milliliters, which is 1 liter is 1,000 milliliters. So we'll times that by 1,000, gives us 0.1 milliliters. So 0.1 milliliters would be really our V1, right? And that's what was added to our V2, which was 2 milliliters, I think you said, right? So that means that our V2 would be 2 milliliters plus 0.1 milliliters, gives you 2.1 milliliters would be our V2. So the only thing we're missing is, what was that concentration one more time again? -6, and that was the diluted one, which would be M2 in this case, right? So we could put everybody into here. That should be something like 7.49 to the minus 6. We want to make sure we use our exponent button times our V2, which would be 2.1, divided by our V1, which would be 0.1. And this would give us a concentration for M1 of roughly, we'll call it 1.57 times 10 to the 1, 2, 3 minus 4. molar. So something in that ballpark would be sort of the answer there. So you need to, again, in terms of the volume though, when you use this, you can use milliliters or liters, but you definitely need to make sure V1 and V2 are definitely the same units. And you got to get the correct total volume because it was added basically to 2 milliliters of water in this case. Other questions that I can help you with here? Okay, so let's talk a little bit about some of this organic stuff that we've been talking about as well. So we've been talking about here at the end aldehydes and ketones, and earlier we also talked about alcohols, and let's just start there. You can make an alcohol through a reaction that we saw when we talked about alkenes, and that's the hydration reaction where we again basically add water to a double bond. And remember that this is the only thing that will change is our carbon-carbon. Double bond will become a single bond to allow everybody to add in. And one guy gets the OH and the other guy gets the hydrogen. So through a hydration reaction here, we go from an alkene to an alcohol. And as we talked about today, this would be ethanol, as there's 2 carbons basically in an OH. We also talked about classifying alcohols, and you could classify again an alcohol as a primary, secondary, or tertiary. And an alcohol can go through a oxidation reaction. And an oxidation reaction in this case means that it's going to actually lose hydrogen, or H2. So if we took a primary alcohol, like our ethanol, and we put it through an oxidation reaction, what happens in this case is we will lose H2. And where the H2 comes from is always this case in the alcohol oxidation. It is always the H that's attached to the OH group, and it's always the H that is attached to the carbon that's attached to the OH group. So those are the 2 hydrogens that will come off. And when those come off, we do get H2. Now, remember that when we draw these sort of results of these reactions, nothing really changes other than right there at those functional groups. So you really have pretty much 95% of the molecule drawn for you. You just got to copy what's there. Obviously, in this case, we take out the H's. So we're just going to copy it exactly the way it looks over there on the left. Obviously, taking our H's out. Now, if you remember when we talked about every time we kind of go from like a single bond, say, to a double bond, to a triple bond, what we always lose is hydrogens, right? So we have to lose those hydrogens to allow the double bond to be made. We lose a couple more hydrogens to allow the triple bond to be made. In this particular case, what happens when we remove the hydrogens is we need to actually put the double bond in. So we need to put a bond in its place. And the bond that forms will always be between the oxygen and the carbon. So where we took out the H's, we replaced with a double bond. And this is what we saw today. This is the aldehyde group. Yeah. So if you oxidize a primary alcohol, you will get an aldehyde. This is again ethanol, OL. This is ethanol, AL here, right? So you primary that. That is how we make an aldehyde. Just like if we took a secondary alcohol like this guy. This is a secondary alcohol. And if we put it through oxidation, which is what the little O means in the brackets there, that's going through an oxidation reaction, it also will lose 2 hydrogens. Once again, it's going to be the same hydrogen. It's going to be the hydrogen that's attached to the OH. It's going to be the hydrogen that's attached to the carbon that's attached to the OH. Those are the 2 hydrogens that are going to go. We'll get H2. Once again, all we need to do is copy exactly what is there and just take out the hydrogens. So copying exactly the way it looks, H carbon, H, C, O, C, H, and H. And just like we did on the top one where we took out the hydrogens, we're going to insert our double bond, and we will put our double bond in there. And that will then make our 3 carbons with an OH, a carbon oxygen double bond. That is a ketone, right? So if you oxidize a secondary alcohol, that is how we make a ketone. By the way, if we go backwards and add the hydrogen to the ketone or the aldehyde, you get back the alcohol. It basically does the opposite. You put the hydrogens back on, take out the double bond, and it goes backwards. That's what's known as the reduction reaction, going the opposite way. Any questions on those there? Now, if we have a tertiary alcohol, such as this guy, and it goes through an oxidation reaction. Once again, we're going to look for our hydrogens here. So we have our hydrogen here, but now when we come to this carbon, is there any hydrogen? There are no hydrogens there, and that's a problem because frankly, for this reaction to take place, you need a hydrogen. So there's no hydrogen there. And that means that tertiary alcohol will not go through an oxidation reaction, so you'll get no reaction that will take place. So because of that, no reaction will basically occur. So you could only oxidize a primary alcohol to an aldehyde, a secondary alcohol to a ketone, and a tertiary alcohol will not oxidize at all because it's missing the hydrogen. Any questions on that there? Now, if we go back to our primary alcohol, which I think we did this guy. And we go through our oxidation reaction like we talked about there. Once again, hydrogen and hydrogen. Make it our aldehyde. If we actually oxidize the aldehyde one more time, we will actually go through oxidation, but it's a different sort of result. And the result is we're going to add oxygen in this case. So not H2, take it out. We're actually going to add oxygen. And where the oxygen will go, it will always end up in the same spot. And that spot is pretty much right there is where the oxygen will end up. So what happens in this case is when you further oxidize an aldehyde, you get the exact same thing. Nothing changes, nothing weird happens other than you insert a oxygen here where the H was. So the oxygen gets inserted. And what happens when you oxidize this aldehyde is it creates this guy, which is also another organic group. This is known as a carboxylic acid. So once again, that is ethanol. That is ethanol, and this is what is known as ethanoic acid, which is a carboxylic acid. By the way, that's also known as acetic acid, also known as vinegar, is basically what that is, but it's also known as ethanoic acid. So we can take our primary alcohol to an aldehyde. You can oxidize it one more time to a carboxylic acid. Now, if you want to do that with our secondary guy, which I think was this guy we did. This is our secondary alcohol, which once again we oxidize to, just like we did on the previous page, basically this ketone here. And you want to oxidize this one more time. The problem is the same thing that we saw with our tertiary alcohol, kind of missing some hydrogen here. So it will not be able to go through that oxidation step. So if you try to oxidize a ketone one more time, you'll get no reaction. Yeah. So the difference between the aldehyde that can be oxidized and the ketone that can be oxidized, are not oxidized, is you can basically distinguish between whether or not you started with an aldehyde or a ketone based on whether or not the oxidation reaction occurs, which I think is sort of the lab this week. So you can determine that if you do go through the oxidation of, say, an aldehyde and it does work, you will know that you started with an aldehyde. If you do the oxidation step on the, say, other solution and it doesn't work, you will know that that is a ketone. The thing that you could use to help you decide whether or not it is that this worked or not is, I think you guys use Benedict's reagent, if I'm not mistaken. They use something like what is known as Benedict's reagent. And Benedict's reagent is really copper 2 that gets reduced down to copper 1. And copper 2 starts out as a blue color. And if the copper 2 gets reduced, that means that the aldehyde would get oxidized. So they always happen together. So something gets reduced, something gets oxidized. And what you will see in terms of color is it will go from a blue color to a orangey reddish color. I think you guys used Benedict's reagent when you did the dialysis bag, right? And yeah, so it'll be the same sort of thing. So if you use Benedict's reagent like you did with the dialysis bag, kind of turns an orangey reddish yucky color. If you do see that color, that means that the copper was reduced. And what that would mean in this case is your aldehyde was oxidized to the carboxylic acid, and would mean that that was an aldehyde that you started with. If you add Benedict's reagent to, say, your ketone when you do your oxidation reaction and it stays blue, that means that obviously the copper was not reduced, neither was your ketone was not oxidized, and you know that that's a ketone. So that is the way in lab you're going to be able to determine the difference between, say, a ketone and an aldehyde. There's other tests as well. One's referred to as the Tollens test. It turns silver. It's like a mirror test. The same idea. The silver gets reduced and it makes this like mirror sort of color. And you know that the reduction occurred. So by default, the oxidation occurred. So in lab, you're going to be looking at that this week, whether or not, you'll have several sort of compounds. You have to decide, are they aldehydes or ketones? And the result of your Benedict's test will tell you that if it's a positive test, then what you started with was the aldehyde. If it's a negative test, then it would have been a ketone. Any questions on that there? Now, just to show you sort of the reverse reaction of the formation of an aldehyde or a ketone. So as we just saw, we can take our alcohol, bless you, and oxidize it here. So this is our primary alcohol into our aldehyde, which again will give us this. It's the same guy that we just drew, plus H2. Now, as I mentioned before, going back this way is actually the reduction reaction. And what happens if you actually did this reaction backwards is you would start with your aldehyde. And you would add your hydrogen. And basically what happens is the exact same reaction that happens with the alkene. So if you remember, the alkene is double bonded, right? Plus the hydrogen, double bond becomes a single bond, and then each one gets a hydrogen. The same thing happens here, except it's not two carbons. It's the carbon-oxygen double bond is where this occurs. So this occurs at the carbon-oxygen double bond right here. And what's going to happen is basically the exact same thing as down here. That double bond will become a single bond. Everything else will remain the same. So you'll have this, everything exactly the same, except that our double bond will now become a single bond, and we will have the H. The reason for that is it now allows the oxygen to have something bind there, and it allows the carbon on the bottom to bind something. And you would put a hydrogen in both places, just like we took it off. We would put the hydrogen there, and we would put the hydrogen back there. I'll just put circles around them. And what we get back is our aldehyde back to our primary alcohol. That is the reduction reaction, which is when you add H2 to an aldehyde. So when you add an H2 to an aldehyde, it undoes it. It puts it back to the alcohol. And the same thing happens when you do it to a ketone. The exact same thing will happen is when you add H2 to a ketone, it will take away the double bond between the carbon and the oxygen, and you'll put back the hydrogens and you'll get back your alcohol. So again, to show you that, I'll do it above here. So instead, if we started here with a ketone, so if we started with this guy here, and we added hydrogen to it, which would be a reduction reaction. Again, hydrogen being HH. This part right here is the only thing that's going to change. And again, we're going to add the hydrogen in, so we need to make room. So we're just going to single bond that guy. And we would end up with this that's now single bonded. And once again, a hydrogen will go to the oxygen, and a hydrogen will go to the carbon. So hydrogen and hydrogen would be added in there. And that would get us back our secondary alcohol. So taking a ketone and adding H2 to it will get you back your secondary alcohol. It's basically the reverse of the oxidation reaction. Oxidation reaction, you take the alcohol to the ketone, reduction reaction, ketone back to the alcohol. And the same thing, obviously, with our primary. Any questions on that there? Okay, so let's try, let's try a couple of things here. Why don't you name this guy here? Let's do why don't we do then do that guy, and then why don't you draw do 3-ethyl butanol and hexanone. Let's do 5-propyl, 3-hexanone. Then let's also do this guy here. All right, so name those guys and draw the others. Left here. So first off, you might want to recognize what you're dealing with. So hopefully you recognize we got a ketone group happening right there. So our longest one that contains that ketone group is 1, 2, 3, 4, 5, and 6. So that's going to be based off of hexane. Because it's a ketone, it will become hexanone. We definitely need to give the location of the carbon-oxygen double bond, which means we would probably want to go this way to give it a 2. So that would be 2-hexanone, which means then at 3 and carbon 4, there would be a chloral. So this then would be 4-chloral, 2-hexanone. Any questions on that one there? Coming to the guy below it, definitely this whole box is the biggest sort of chain. It also has the double bond there. And once again, it is a carbon, carbon, carbon with a double bond in the middle carbon. So this also is a ketone as well. That is a square, which is basically cyclobutane, which means that this would become cyclobutanone. Once again, because this is a ring, you don't have to give the location of where the double bond is, but it definitely is going to be carbon number 1. And that means, I think in this case, either way, you will get to carbon number 3 there for your methyl group. So that's going to give you 3-methyl cyclobutanone. Any questions on that one there? Looking at our guy in the top right here, you hopefully should recognize this is carbon-oxygen double bond to a hydrogen. So that's an aldehyde group that we're looking at there. That's at the end. That means that this really is carbon 1 to carbon 2 to carbon 3 to carbon 4. And that's going to be based off of butane here. And since it is a aldehyde, it will be butanal, Al. Remember, again, you don't need to give the location of this carbon-oxygen double bond, but it definitely is going to be carbon number 1. That means at carbon number 2, there is a methyl group. And at carbon number 3, there is a chlorine group. In this case, we do go alphabetical. So this would be 3-chloral, 2-methyl, and butanal. Any question on those names there? Yeah. Butanone, yeah. Well, we know this is definitely a ketone because this is a carbon, that's a carbon, and that's a carbon, and that's a middle carbon that has the oxygen double bond. So that's the 3 carbons in a row with the double bond. So that definitely is a ketone. Now, in terms of an aldehyde on a ring, you actually will a lot of times see it like this, kind of hanging off of it like that. So because you need the H, so there's no way to incorporate that in the ring. So usually the aldehyde group in sort of a ring type of situation would actually be found outside of it. And really, again, where that group would be attached, this would be carbon number 1 on the ring in terms of that. Yeah. Other questions? Okay, so drawing here, butanal. So the Al tells us it's an aldehyde. the butane tells us it's 4 carbons. So we're just going to start with 4 carbons. And again, you can put it on either side, but it is the aldehyde group, which means it definitely should always end up at an end. So either the right end or the left end. That takes care of that. That definitely is carbon 1, which means that's carbon 2. So carbon 3 would be here. And that's an ethyl group, which is a 2 carbon group. And then I can put in some hydrogens here. I didn't leave a lot of room, so let's try to squeeze them in. 1 hydrogen there and 3 there. So 3, 1, and 2 in terms of the hydrogens. Any questions on that one there? All right, last one here is hexanone. So ONE tells us it's a ketone. Hex tells us it's 6 of them. So we'll go 1, 2, 3, 4, 5, and 6. 3-hexanone tells us a carbon number 3. That is where the double bonded oxygen is at. And because I call that number 3, my number 5 would be over here, which is a propyl group, which is 3 carbons, which will look something like this. And now we can fill in all the rest of the hydrogens here. This guy would need 1. This guy would need 2. This guy needs none. 2 and 3 in this case. Yeah. So there you go. Any questions on any of those there? Any questions on anything else? Okay, if you still have questions, feel free to hang out. Otherwise, have a good night.